In this chapter, we introduced Newton's laws of motion, which involves force and dynamics and a lot of other things. Newton did a number of things. The one that he is known the most for is his Philosophiae Naturalis Principia Mathematica. This is where he outlined the mathematical principles of natural philosophy, which is what they called physics back then. So this is the underpinnings, the mathematical underpinnings of physics that he lays out in this book. Now, Newton didn't think this would ever become anything important, and so he went on to get a new job, or a real job, as he would have called it, after he played around with this for a while. So what does this involve? Well, one of the things it involves is forces. And one of the things you have to get in your head is force, like velocity. Force is a vector, right? Force has both a magnitude and a direction. And you're familiar with this. You're familiar with this in your everyday life. You don't really think about it this way, but all the forces that you exert, all the forces that get exerted on you, they all have both a magnitude and a direction. Gravity is a force that it gets exerted on us, and that's what our scales actually measure. They don't measure our mass. They measure the force of gravity on us. So if I were to take my scale to the moon, it would show that I weigh a seventh of what I do here on Earth. Am I suddenly very skinny? No, I'm not, right? I'm actually have the same mass. So what we measure when we weigh ourselves is the force of gravity on us, and gravity actually acts on every single bit of us all at the same time. Unlike most forces which are distributed in some different way, gravity is much more fundamental. So, what is Newton's first law? So, Newton's first law of motion is this: a body at rest remains at rest unless acted upon by an outside force, and a body in motion remains in motion at constant velocity unless acted on by a net external force. So, there's a key word in here: external force. All right? So this puppy here in this chair has no net external force exerted on him. He has the downward force of gravity, but that is exactly canceled out by the upward force of the chair on the puppy. So the net external force is zero, right? Net external force is zero because gravity and the chair oppose each other and cancel each other out. So whenever we talk about forces, we're always talking about the system, and Newton's second law applies to that. All right. When we look at a system or when we look at a problem, we have to determine where the boundary is. All right. Without a boundary, the net force is always zero because there is nothing external to the universe acting on us. Right? I mean, if you don't have a boundary, we're talking about the whole universe. There's nothing outside the universe acting on us. So the net external force is always zero if you have no boundary. But we apply boundaries all the time. We can apply a boundary around just the wagon with the kid in it, right? And we can have that as our boundary, or we can extend the boundary and draw it around the other kids, right? The other kids pushing the wagon. So there are different ways to draw these boundaries and different ways to think about them. And that's one of the things we'll learn throughout working the problems for this chapter is where are these boundaries. Newton's second law also says this, and this you've probably heard before. We usually state it as force equals mass times acceleration. Newton stated as the acceleration of object is the net external force on it divided by its mass. All right, so he said it this way. Down here, we typically say it this way: F net equals mass times acceleration. So I'm sitting in my chair. All right, again, gravity is acting on me, but my chair is exactly countering gravity, so the net force is zero, so I'm not accelerating. Now, were my chair to fail and no longer fully support my weight, I would accelerate downward because the net force downward would no longer be zero. All right, and so the net force would mean I would actually accelerate. So gravity comes into play all the time. We usually talk about gravity in terms of the acceleration of constant g, right? And the weight, our weight, that when we get on the scale is our mass times this g. Now this is why when you sit on a scale, get on a scale that reads out kilograms. Kilograms is mass, right? Kilograms is mass. But for the most part, this g is a constant. So when a scale measures your weight, it converts to your mass by dividing through by g, right? And converts the weight to the mass. Now, in our English unit, pounds is actually a force. Pounds is not a mass. Pounds is a force. If you want to know your mass in English unit, you need to learn about stones and figure out how many stones you are. Of motion is that for every action there is an equal and opposite reaction. And so whenever we're looking at a system, like we look at this, the boundary of this system, there is a force that this woman, this doc or lab technician, is pushing on the cart, and there is a force the cart is exerting on her. All right? So they're exerting a force on each other, just like I exert on a force on my chair through gravity. My chair exerts a force on me. There are equal and opposite forces all over the place. But when we start talking about the system, right? When we start talking about the system, we can end up with a net external force to the system. All right? Here we are. This woman is pushing backwards on the floor. The floor is pushing forward on her. The woman pushing backwards on the floor, well, that's internal to the system, but the floor pushing forwards is external to the system, right? So that ends up giving us a net force on the system going this way, and then here, this is the force of friction on the wheels. That's also an external force. If the force of the floor forward is greater than the force of friction, then this whole cart will move. All right. We will look at types of forces in just a moment.